So then it's time for our second talk. So I have the pleasure of introducing Sibylle Driezen, who will tell us something that covers, or that fits quite nicely with the theme of the conference. So something about integrability and dualities, and this applied in the context of string sigma models. So please go ahead.
Thank you. So first, of course, let me thank the organizers for giving me the opportunity to present this work and the organization of this nice conference. I'm sure the rest of the week will be great. So I will talk about work that I did in the last 1.5 years or so, which consists of two main topics, two research lines that I did together. Both of them I did together with Riccardo Borsato, who is also here. And then a number of collaborators, including Falk Hassler, who is also here, Luis Miramontes, and Juan Miguel Nieto, who should also be here, and then Leander Ruiz. So the two lines or topics that I will be discussing, so the first one consists of the question to understand when we have a supergravity solution, if we could generate new 10-dimensional supergravity solutions. And there's several transformations now that are able to do that. And so we want to understand how, if there is more options, if there is some room to wiggle. And as I will show you in the talk, we will do that by reformulating the problem in some efficient way. And interestingly, this way of reformulating it tells you that at the same time, these transformations will also be canonical transformations at the level of the worldsheet that gives rise to this supergravity background. And this brings me to the second topic, namely, if you would have an integrable sigma model, if you have a transformation that is a canonical transformation on the worldsheet, then you would also generate a new integrable sigma model. And we will use the fact that we have a canonical transformation to treat this undeformed model and this deformed model at the same footing, as I will show you. Now, the broad motivation to have in mind is that generating supergravities or generating integrable sigma models gives you some sort of organizing principle for these theories, so in the landscape of string vacua, if you want, or in the landscape of integrable theories. Now, we know very well that if we deform such models, that in general we get some very complicated backgrounds, also some complicated worldsheet theories. But because we preserve integrability, we still have a high level of analytical control in principle. So at the same time, also there's, this is because of course we know several integrable methods to solve your theory. And so looking at this generation of new integrable models allows you to perhaps generalize also these integrable methods to these more general cases. Now, more directly from the point of view of holography, we are of course interested in this because these transformations that preserve supergravity and integrability are very interesting to possibly generalize ADS-CFT, namely possibly breaking some supersymmetry and maybe some conformal symmetries while you're still having this analytical control of integrability. Okay, so as a proof of concept of these two topics, so generating supergravities and integrable models, I will focus in this talk on the homogeneous Yang-Baxter deformations. So they have these two properties. And they're also interesting because they capture the very well-known TsT-transformations, and they generalize this to a non-abelian setting, as I will explain. So in the talk, I will show you why these homogeneous Yang-Baxter deformations are supergravity solution-generating techniques, how you can very efficiently see that they are supergravity solution-generating techniques, and using this reformulation to classify similar transformations that have this property. Then, as I said, they will at the same time be canonical transformations at the level of the worldsheet, and I will use that to treat the deformed model and the undeformed model at the same footing at the expense of generalizing your boundary conditions of the worldsheet. So I will explain that further. And this in particular has been very useful for us to apply the method of the classical spectral curve and its semi-classical quantization. And this we applied in work that appeared today at the archive to obtain the semi-classical spectrum of a particular Jordanian deformation of the ADS5 cross S5 superstring. And I want to stress that this is a first principle computation without any conjectures based on symmetries. Okay, so before I do that, let me review these very interesting TsT-transformations and tell you why they are so interesting. So what are their attractive features? So we imagine that we start with some worldsheet sigma model that I give here. And we imagine that it corresponds to some integrable sigma model that gives rise to a 10-dimensional supergravity solution. And in addition, we assume that the background has two abelian isometries, so one in x1 and one in x2. So it's hard to point it. Okay, so if you have these abelian isometries, then you can apply a TsT transformation. And so what this is just a usual an abelian T-duality along one of the abelian coordinates, a shift in the other coordinates, and then a T-duality transformation back to your original coordinates. Now, if this model is also a supergravity, then this means performing this transformation, you will generate a new supergravity background, as is very well known, because this just involves abelian T-duality and some coordinate redefinitions, and this is, of course, a symmetry of string theory. So you generate a new metric and a new B field that depend on this deformation parameter, eta, where eta is involved in the shifting of these coordinates. Sorry if I'm not able to point very well, so I hope it will be clear enough. Now, as I said, this is very well known, but it's very nice to see this in the language of double field theory. And for the rest of this talk, the only thing that you should know about double field theory is that it is simply a reformulation of supergravity with some manifest global ODD symmetry. In particular, you go to some doubled space where you have this doubled sort of symmetry, this ODD, where D is a number of the original space-time dimensions. And your field content is then packaged into some doubled objects. So in particular, the metric and the B field of usual supergravity, the G and the B here, they're packaged into this doubled matrix, which is called the generalized metric. And they are packaged in this very particular way. Now, if you perform a TsT transformation, you know how the metric and the B field changes, so you can construct this new generalized metric, and you see that what happens is just that you're simply transforming the original generalized metric covariantly with this object S, where S is this matrix of upper triangular form, and beta is some antisymmetric matrix which depend on this deformation parameter eta. And so that is an element of ODD, and it's a constant element of ODD. And we call this a beta shift, a global beta shift. So you can think of TsTs as just global beta shifts. And because, of course, as I said, double field theory has this manifest global ODD symmetry. If you start from a solution that satisfies the supergravity equations of motion and therefore the double field theory equations of motion, and you apply this transformation, the generalized metric is just transforming covariantly, and then after this transformation, you will still, because it's a symmetry, you'll still solve the supergravity equations of motion. But what is very important is that it's not a trivial transfer. It's not a trivial symmetry transformation at the level of the supergravity background fields. So the generalized metric is transforming covariantly, but it is scrambling the notion of the metric and the B field inside, because it's transforming with this upper triangular matrix. So if you read off the new matrix G prime from this object, you will see that it's some scrambling of the original metric and original B field. So to conclude, we already have here supergravity solution generating techniques, and they're captured by non-trivial global ODD elements. So an example is these TsT beta shifts, and another example is, of course, abelian T-duality, where this transformation matrix S is of this off-diagonal form. Okay, so that is the first interesting feature of a TsT transformation. The second is that, of course, performing T-duality shifts and T-dualities at the level of the worldsheets, they are just canonical transformations and they preserve integrability. Also, this is very well known, but it's very nice to see this at the level of the currents. So I told you to perform a TsT, you need these abelian isometries in x1 and x2. And it turns out that, so you can associate to that some abelian neuter currents for the original model and for the deformed model. And it turns out that on shell, they equate to each other, they coincide with each other. So they satisfy some particular relations in terms of the coordinates, in terms of derivatives of the original coordinates and derivatives of the new coordinates. And these abelian neuter currents, they coincide. And this, so I didn't write it down, but it applies particular relations of this form where we have the spatial derivative to the worldsheet space coordinate sigma of the new coordinate x prime minus the spatial derivative to the coordinate sigma, worldsheet coordinate sigma of x1, and that should be equal to the neuter current, the time component of the neuter current of the second abelian isometry, and the same happens for these other coordinates. And so this implies that if you integrate this relation and you assume that your new background just satisfy periodic worldsheet boundary conditions, then you will have, for the original background x1, you will have twisted worldsheet boundary conditions. And in particular, so we integrate this, we have this periodicity constraint for the new background, but for the original background, the worldsheet boundary conditions, this is not zero, but it's given by the integral of the neuter currents, which is just a neuter charge, okay? So, and then we get this very nice picture here, where you can think either in the deformed picture, where the metric is deformed, so you get this sphere, which is a bit squashed. The metric depends on the deformation parameter, but the worldsheet, the string, if you go around the spatial coordinate, you just come back to the same value. And this is on-shell equivalent to an undeformed model where the space-time does not depend on the deformation parameter, so it's just some sphere here. But at the level of the worldsheet, the non-trivial information about the deformation is captured by this twist. So if you go around the worldsheet, you will not end up at the same point, but there is some twist, which I denote by these stars. So as you see, this is already known since 2005, so it's a very nice story that is well understood. So just to summarize, these are the main features that I want you to remember. Of course, to generate a new supergravity solution, we just need to assume that this guy is a supergravity. It doesn't need to be integrable. And then to preserve integrability, we only need to assume that this is integrable. And then, of course, you can have the same things at the same time. Okay, so please interrupt me also for questions if there are any. So now I will generalize this. I will show how these nice features generalize to the homogeneous Yang-Baxter deformations. Okay, so the homogeneous Yang-Baxter deformations, I will show them here for the PCM, for the principal chiral model for simplicity. The principal chiral model is obtained when you send the deformation parameter eta to 0. And then you recognize just the normal action of the PCM, where the metric is just some nice group manifold. So here we parameterize this in terms of group elements G, and you obtain the normal sigma model of this form when you introduce some parameterization in these group elements in terms of coordinates. And so turning on the deformation parameter gives you that you stick this particular operator inside, and so that will deform the metric and the B fields. So you get some new expressions that depend on eta. So I told you what is a deformation parameter, but I didn't tell you yet what is this object R, which is called a R operator, which is acting at the level of the Lie algebra of this Lie group. So it's scrambling the generators of the Lie algebra in some particular way. And it satisfies two important conditions, which we will see coming up during the rest of the talk. So, and they are really the defining properties of a homogeneous Yang-Baxter deformation. The first one is that it satisfies a classical Yang-Baxter equation, which is of this form, and that the guy R is antisymmetric. Now, this is a non-abelian generalization of the TsT-transformation because this R operator can act non-trivially on a non-abelian algebra G. So the Lie algebra G can be non-abelian. You reduce back to the case of TsT when the algebra where the operator is acting on is abelian. So you get we call it an abelian R matrix. And this is just related to the fact that you would have some abelian isometries on which this guy is acting. Okay, good. So now, as I said, the metric and the B-field transforms, of course. And the transformation rules are, again, very nicely captured in the language of double field theory. So again, what happens is that the generalized metric transforms covariantly with some object S. Again, this object S is of upper triangular form. Where beta is an antisymmetric matrix, so it's an element of ODD. But now, beta here depends on the coordinates, so it's not a constant. It's not a constant object anymore. And in particular, we see here that we have these, so it's constructed out of the killing vectors of the background, which are associated to the non-abelian isometries. So of course, if you have a non-abelian isometry, the associated killing vector depends on coordinates. If you have an abelian isometry, the killing vector is just constant, and then you reduce back to the TsT case. So then this beta becomes this guy here. So homogeneous Yang-Baxter deformations can be seen as local beta shifts. Now you can ask me, well, you told me that double field theory has global ODD symmetry. It doesn't have local ODD symmetry. So why would I still preserve the fact that you have a supergravity? And the reason is that the double field theory equations of motions, they have other symmetries, as I will show. So these other symmetries, they are most conveniently seen in the language of the flux formulation of double field theory. This is just a reformulation in terms of Vielbein. So you go to some Vielbein formalism for the generalized metric H, where E is this generalized Vielbein. And in this formulation, you can construct two interesting objects, which are called the generalized fluxes. They are this particular combination of the generalized Vielbein. So once you have the Vielbein, you can just compute the fluxes straightforwardly. And then you have also this other flux, which only has one index, constructed from the Vielbein, and also an object D, which is called the generalized dilaton. And it's just a combination of the usual dilaton of supergravity and the metric G. Now, in the flux formulation of double field theory, the key point is that the action of double field theory, as well as the equations of motion, can be completely written in terms of these two fluxes, so the flux FABC and the flux FA, as well as their derivatives. So, if you would have a transformation that is transforming your background non-trivially, so here in the flux formulation, it's transforming the Vielbein covariantly with this object S. So at the level of the generalized metric, is transforming this in the same way as before. So the background gets deformed, but if you find that your original Vielbein gives rise to a flux FABC, and the new Vielbein gives rise to a flux F prime ABC, which coincides with the original flux, as well as for these other guys, then you would still solve the solutions of the double field theory when your original model is solving those equations of motion. But as I said, you are scrambling metric and B-field, so you are transforming the background non-trivially. And so this particular transformation happens for homogeneous Yang-Baxter deformations if this operator R satisfies these two defining properties. So if it satisfies the classical Yang-Baxter equation, and if it's antisymmetric, then the flux with three indices will remain invariant. If also the flux with one index remains invariant, and you assume that you just go to normal supergravity with a normal dilaton and so on, then you find that the R operator also has to satisfy this condition, which is called the unimodularity condition. It's just some contraction of the R matrix with the structure constants of the Lie algebra. Okay. Good. So what we then did in one part of our work was to look at these transformations and try to classify them and see if there are some more general transformations that satisfy these conditions. And of course, as you know, if you want to do a classification, you have to make some assumptions. So we did the same. So we assumed a generalized Schwarz ansatz, which is just a fancy name for us to say that you can decompose your manifold into some external part and some internal part. And the solution generating technique is only acting non-trivially on this internal manifold. In addition, you assume that on this, so the fluxes will decompose in this external part and this internal part, and you assume that the fluxes on the internal manifold are just constant. And in that case, you get a lot of power. So what happens is that identically, you will see that this flux with 3 indices just satisfies a Jacobi identity. And therefore, you can associate some Lie algebra to it. So I will not go into the detail because I want to cover many topics. But the main point is that you have some doubled Lie algebra which you can use to really find out which are the transformations that are changing your background. And what we find is something very similar as before. So we find that the transformations that change the background are ones that act on this Lie algebra with this upper triangular matrix. So now this guy is a constant transformation because it's just transforming this Lie algebra, well, scrambling these generates of this Lie algebra amongst each other. But it's also of this upper triangular form. And then you also have the T action, which is of this off-diagonal form, and a combination of them. So we find some particular conditions for when this flux with 3 indices has to stay invariant. We get some conditions of this form. Here we have fluxes with lower and upper indices in various places. They are just different components of this flux with doubled indices. In particular, in this case, we get this zeta matrix. It's an antisymmetric matrix. You can multiply this with a deformation parameter, and so these guys capture deformations or integrable deformations, as I will explain. Now, from demanding invariance of the flux with 1 index, and again, demanding that you can extract some dilaton, so you get some usual supergravity, you get some additional conditions so that you remain in supergravity. And this particular equation that we have here, we classified this in our work with Falk by Lie algebra cohomologies of some particular subgroup of this doubled Lie algebra. Now there's also some freedoms that I didn't discuss. I will not go into more details, as I said, but please, during the rest of this week, you can ask me more about this. Okay, so now, as I said, these particular transformations, I said in the beginning, they're also canonical transformations at the level of the worldsheet, and so now I will tell you why that is. So we go back to the level of the worldsheet, so we go back to some worldsheet sigma model here, and we go to the Hamiltonian formulation, so we construct the canonical momenta, etc. What we can do is go to some sort of doubled space again, so it's very reminiscent as before. We can package these canonical momenta with the usual coordinates of the usual bosonic fields. And we dress that with some object E, which is exactly the same one as we had before. So it's some combination of the metric and the B field. And in that case, you see that canonical Poisson brackets between momenta and coordinates can be rewritten in terms of this guy psi A in this particular way, where we again see this flux appearing. So it's precisely the same combination in terms of the Vielbein that we had here. So it's exactly the same expression. And that is the only one that has some dynamical content. So this means that if you have a transformation that is changing your canonical data, so sending a psi A to psi A bar by changing your background, sending this generalized Vielbein to a new generalized Vielbein, but it would leave this flux with 3 indices invariant, then you would have a canonical transformation because you're preserving the form of the Poisson brackets. Now, I should emphasize that this is not a standard canonical transformation. It's not just reshuffling the canonical coordinates. It's a canonical transformation up to worldsheet boundary conditions, and this is very important. So the non-trivial information about this deformation will be captured in the worldsheet boundary conditions, as I will show you. Now, for homogeneous Yang-Baxter deformations, this happens when these two properties are again satisfied. And so as you see, we have less conditions here. So supergravity solution generating techniques are more strict. There we had also the invariance of the flux with one index. So here we see that we have more canonical transformations on the worldsheet than supergravity solution generating techniques. But every supergravity solution generating technique, all the ones that we consider, are also canonical transformations at the level of the worldsheet. Okay, so now let's see how this happens for homogeneous Yang-Baxter deformations. So I want to use this canonical transformation to really treat these two, the undeformed model and the deformed model, at the same footing. So I want to compare the undeformed model with the deformed model, and to do that, I will use a different parameterization for the principal chiral model. So I have some group element G tilde, and then I have a parameterization G for the deformed model. Okay. Then it's very nice to see that everything that you want to know about your worldsheet sigma model, namely equations of motions and lax connections, if you have them, they can be very conveniently written in terms of currents. And so here for the principal chiral model and the homogeneous Yang-Baxter, we have some currents associated to a right-acting symmetry. So it's transforming this G tilde to G tilde times an object in the group. And a neutral current associated to that is just a Maroux-Cartan form. And so in terms of the group elements, it takes this form. For homogeneous Yang-Baxter, we have the same symmetry, and the neutral current associated that is this guy, so it's a different expression. It involves the deformation parameter and this object R. But what is nice is that, so if you write down the equations of motions, they just look completely similar. So it's just a divergenceless property of these currents, and you can replace G tilde with A if you want. Also, the canonical variables, they are completely similar upon changing G tilde with A. And that is precisely what the canonical transformation is doing. So sending the canonical variables means that you're just replacing G tilde with A. And we know that it's a canonical transformation, that it satisfies the correct Poisson brackets if these two properties of homogeneous Yang-Baxter deformations are satisfied. Now, concerning integrability, this is nicely seen at the level of the currents again. So we have some conserved currents, and we know very well that if they are also flat, then we have classical integrability. And so flatness means that the current satisfies this condition, which for the PCM is just an identity. But upon changing G tilde with A, we find that this guy is also flat as it should. If these two conditions are satisfied, and also if you assume the equations of motion. So we get a lax connection for the PCM in terms of G tilde, which is just transformed to the homogeneous Yang-Baxter as this way. So just to say that we can have some on-shell equivalence between these two models when you're just equating these two currents with each other. So J tilde in terms of G tilde with A in terms of G. Now, of course, if we look at these expressions, we know that they are not identically the same in terms of if you express them in terms of the group elements. So what you need to do is to introduce some twisting if you also want to relate the coordinates with each other. And so this twist that we introduce is the guy here. So G equals F, which is the twist field. Oh my God. With G tilde. Yes, okay. And this implies some twisted boundary conditions, as I will show you. So we have this expression. If you assume for the deformed homogeneous Yang-Baxter, if you assume periodic boundary conditions, which is something normal to do because we already have a deformed space-time, but if you assume that then the group element of the undeformed model will satisfy some twisted boundary conditions. And they are given particularly here, so where W is the twist. So now, thinking back about the TsT example, here we have some nonlinear relations for the twisted boundary conditions in terms of the coordinates, x tilde, because here we get just a relation in terms of the group element. And before for TsT, it was just some linear relation that was given by a conserved charge. Yes?
Does it depend on G tilde or it's universal?
So I will tell you that it is. You can construct it from G tilde, but it is constant. You can show that it's constant. So it is dictated by some conserved charges. But I will tell you that right now. So this particular observation was already known for quite some time. The problem with it was that people never use it really for practical purposes. And the reason is the following. So if you go to the homogeneous Yang-Baxter picture, where you write everything in terms of the group element of the deformed model, and you equate these currents, then you find some very simple relation between the twist field. I don't know why this, should I do it like that? Or? Okay, so you get this particular relation where between the twist field and the group element, and you see that the variables are very nicely separated. You can just very quickly write down a solution for this equation, a solution for this twist field. And the solution is given by a path-ordered exponential of an integral of this object phi that was defined above. So it's very easy to write this solution, but you have a price to pay. So in particular, this expression is highly non-local because it involves a path-ordered exponential. So if you expand the exponential, you get some integrals of integrals of integrals and so on. And secondly, it's also quite an unnatural expression because it's written, the twist field is written in terms of the variables of the deformed model. So you're saying that you have some deformed theory with periodic boundary conditions that is on-shell equivalent to some undeformed theory with twisted boundary conditions, and a twist is given in terms of variables of the deformed model. So it's kind of unnatural. But it was easy to write down, but yeah, anyway, because of these two problems, it was not used for practical purposes. Now, what we did in the work with Louis was to rewrite this in terms of the PCM picture, so the variables G tilde. And then you get some relation that I write down here, which looks a bit more complicated because you get some relation between the twist field and G tilde, where the twist field and G tilde are not separated nicely. And I think that is the reason that it was not looked at in detail before. But what we did was to use properties that we know of homogeneous Yang-Baxter deformations, namely that they have some two co-cycle in them. Namely, if you invert the R operator, you call this W, then W is a two co-cycle due to this classical Yang-Baxter equation. And two co-cycles in the algebras have been studied for quite some time. They satisfy a lot of properties, and we use those properties to solve this equation in terms of the twist field. Now, let me just mention that we were not able to write down a closed expression for a general R matrix, but we are able to write down a closed expression once we specify the R matrix, because the R matrix is just acting on some finite dimensional algebra, and so you need to solve some finite number of equations, which can be done rather straightforwardly. So once this R operator is specified, you get a closed expression, which is local. There's no path ordering involved anywhere. And it's written in terms of the variables of the undeformed model. So it's a more natural thing to work with. Okay, so we get again this picture of the deformed spacetime with periodic boundary conditions and an undeformed spacetime with twisted boundary conditions, W. And of course, if we take eta to 0, the deformation parameter to 0, then we can just a truly undeformed picture where both the spacetime and the worldsheet boundary conditions are the usual ones. Okay, so now let me show you how you get some closed expression for a particular case. So we look at here at Jordanian deformations. There are particular examples of homogeneous Yang-Baxter deformations, which you can write down once you have an SL2R subalgebra in your problem. So the SL2R subalgebra is given in terms of generators H and E plus and minus. They satisfy these commutation relations. And the algebra admits an antisymmetric solution to the classical Yang-Baxter equation. So here I write it down in a fancy way, but just the guy is just acting on the generators in this particular way. And then the expressions that we find can easily be inverted, and you can write a closed expression for the twist field, which I write down here. So it's given in terms of two objects, big Q and small q, which are written in terms of an object y, which in turn, so y in turn is found by the variables G tilde of the undeformed model. And in particular, so if you have a solution of your sigma model, you can just plug everything in and you will find what is the twist associated to your deformed model. Okay, and so this we have used in the work that appeared just today. to apply a Jordanian deformation to the ADS5 cross S5 superstring. So here I was, I think, I was a bit quick here, so here I should write down the supercoset sigma model. Basically it just involves inserting some projectors, etc. But just to say we have some sigma model where the Lie group G is, of course, the one of ADS5 cross S5, so it's PSU22/4. Okay. And this superalgebra admits an antisymmetric solution to the classical Yang-Baxter equation of Jordanian type. So it's of this form, where now E plus and H are just some particular combinations of the conformal generators of ADS5. Of the conformal algebra. So we have the dilatation operator and the boost, and then the canonical, the momenta operators. Okay, so this guy solves the classical Yang-Baxter equation and is antisymmetric, so you know that at the level of the worldsheet you preserve integrability. And it's also a supergravity solution generating technique, so in particular it's unimodular when you include this fermionic tail. So Q1 and Q2 are some particular supercharges of PSU224. If you don't have this fermionic tail, you still have a solution to the classical Yang-Baxter equation, and so you still have an integrable worldsheet. Okay, so now applying this deformation to the ADS5 superstring, ADS5 cross S5, we get a deformed metric that depends on the deformation parameter. In particular, the deformation is only acting non-trivially on the ADS5 part, so we just have here the round 5 sphere, and then we have the deformed ADS5 background. So I've written them down here in some unusual coordinates. They are global coordinates, which we specifically checked. And they are global coordinates for every value of the deformation parameter. So I want to emphasize this a little bit because, of course, we have global coordinates for undeformed ADS5 cross S5. But once you introduce a deformation, the causal structure of the spacetime may change. And so these original global coordinates are perhaps not good global coordinates anymore. And in fact, we see that a lot of isometries in these original global coordinates get destroyed, so they are not useful in this case. Here we find that the change of the deformation with what is called Schrödinger spacetimes is just this particular highlighted term. And Schrödinger spacetimes have been studied quite a lot in ADS-CFT, and also global coordinates are known for them. So what we did was to apply the transformation to global coordinates that was known for Schrödinger spacetimes, and then we checked if they also for this case are still geodesically complete. And so it is the case. And this was important for us because we wanted to have a global time coordinate T that in which we also have an isometry, so that we have a well-defined global energy associated to our problem, and that we will use to compute that we will use to in the spectral problem. Okay, yes. So this is already in the global coordinates. The Poincare patch is obtained once you do the transformation back. So these x plus, small z rho, small theta, and x minus are the Poincare coordinates. Okay, so now I will go to the fact of trying to compute a spectral problem, and for that we want to look at a particular solution of the equations of motion of your sigma model. And of course, it's very useful to mimic what you do in the undeformed case. So you want to try to understand and study the most simple solution, namely a BMN type solution, which is a point-like string. So what we did was to have some point-like ansatz, and then the equations of motion can be very easily solved. And we find that, in particular, this time coordinate goes with the worldsheet time tau, with some rates a, where a is a constant. V also goes with tau with some constants involving the eta deformation parameter, and then some constant b, and then z just stays constant along tau. And of course, these satisfy periodic boundary conditions. Now what you can do is to translate to this twisted picture. We do this you have to be careful with some gauge ambiguities from PSU224, which we discuss in our paper, but eventually just end up with some solution written down here, which in particular depends on the sigma coordinates. So z tilde depends on the sigma coordinate in this way. So we get some extended string solution in the twisted model. And these satisfy periodic twisted boundary conditions associated to the Jordanian twist, where the charges big Q and Q are given by this form. Okay, now I want to briefly take a moment to emphasize what is the advantage of using this twisted model rather than the deformed model for computing the spectral problem. So we have a flat Lax connection because we have an integrable model, and so that means that you can construct what is called a monodromy matrix, which is a disperse-ordered exponential. And this monodromy matrix has some constant eigenvalues. So the eigenvalues give you conserved charges, and so you get an infinite tower of charges when you expand around particular values of the spectral parameter Z. Now, in the undeformed periodic picture, so the truly undeformed picture, you have some unbroken symmetries. And if you look at asymptotics of this monodromy matrix, so you expand around some infinite value of the spectral parameter, you find some conserved charges that are associated to the usual Noether's charges. So they are particularly this QL. And they are particularly of local form, so the asymptotics of the monodromy matrix has some local conserved charges. In a deformed picture, the truly deformed picture where you have periodic boundary conditions, this gets completely scrambled. So basically, you look again at asymptotics of this monodromy matrix, and you find that if you expand around Z infinity, you find some very involved expressions which are highly non-local. Because of this path-ordered exponential, basically, even every term, even the first order term in the expansion, it will be a highly non-local expression. And this is something that you cannot use in your spectral problem. So because you really want your asymptotics of the monodromy matrix to have some local conserved charges. Now, in the undeformed twisted picture, things become nicer. So if you look at the asymptotics of the monodromy matrix, you will see that it involves some local expressions that involves also the twist. So it encodes information on the twist, as well as the next order is a local expression. It doesn't involve conserved charges, but it will involve conserved charges when you diagonalize the monodromy matrix, and in particular the asymptotics. And this brings you, so you can really look at the asymptotics, really try to understand the spectral problem because you have these local charges. So, and it brings you to what is called the classical spectral curve, which you find by diagonalizing this monodromy matrix. We introduce some quasi-momenta, PZ, which are related to the eigenvalues of the monodromy matrix in this way. Now, in an 8x8 representation of PSU224, you will have 8 quasi-momenta. 4 will be related to the ADS space, so this is P hats. And then you have P tildes, 4 P tildes associated to the sphere. Now, as I said, if you expand around the asymptotics, you get conserved charges. In the truly undeformed case, in the untwisted case, you get the Noether charges in the Cartan of PSU224. And in the twisted case, you get eigenvalues of this twist, as well as the Cartan charges of the remaining symmetries of the twisted model. So in particular, because these twisted boundary conditions, they will reduce the number of symmetries, but here you will find that the Cartan charges of the residual symmetries appear in the asymptotics of the monodromy, of the eigenvalues of the monodromy. And for our Jordanian deformation, we find here in particular the charge related to the global energy, as well as a charge related to an isometry in angular coordinates, so it's some spin charge. And then we see also the charge Q, which is dictating the information about the twisted boundary conditions. Now, for our particular solution, you can compute these quasi-momenta, and you will see that they take this particular form. So I only wrote down the ADS5 quasi-momenta because they are the ones that non-trivially get deformed. And so what you should, for the classical spectral curve, we think of each of these quasi-momenta as some sheets, some Riemann surface, which for particular solutions share some cuts. So for our particular solution, we see that the P hat 1 and the P hat 4 they share a square root branch cut, and then P2 and P3, they also share this square root branch cut. Okay, good. So having these particular local charges in the asymptotics allows you to perform a well-known method put forward by Gromov and Vieira in 2007 to semi-classically quantize this spectral curve. And this method still applies to our case, so to the twisted model, up to some minor modifications, namely the modifications in the asymptotics of the quasi-momenta. And so the idea is to introduce excitations, quantum excitations on this cut in the form of microscopic cuts that we think of as quantum poles. So in the classical limits, so the full cut can be thought of as a condensation of poles. And when you put an excitation to it, this gives you some quantum correction to the charge. So we send P to P plus some quantum delta P, okay? Now, the interesting thing is that coming from the properties of the classical curve and also properties of PSU224, there are a lot of, there are very restraining properties also for the quantum excitations. I will not go into any details, but let me just tell you that they are restrictive enough to completely fix these quantum corrections. In particular, you can completely fix the poles where you can put the excitations, and you can completely fix their residues. And this allows you then, so you can fix them after doing just some algebra. It's rather straightforward, but it's quite some work. And this then allows you to compute the corrections to these local charges here. In particular, the correction to the energy. And you do that by modeling the fluctuations as some harmonic oscillators, as we know very well. And then we find a one-loop correction on top of the classical the classical energy. Sorry, I didn't specify that, but for a particular solution, we have this global energy, which is just given by this A coefficient, which is determining the rapidity of this T coordinate. And so you can compute the one-loop correction on top of that. So that will depend on the classical energy A. So this coefficient A, and it will also depend on the deformation parameter as well as this parameter B that was a parameter that we had in our classical solution. Now, interestingly, we also see that the charge related to the twist that appears here does not receive any quantum correction. So it's sort of protected to on loop to quantum corrections. And this is quite interesting because it tells you that your twisted model is quite robust to quantum corrections. Now, let me also emphasize that we performed some particular checks. So if you turn off the deformation parameter, you won't have any correction to the energy, which is something that we know from BMN, and also from some explicit computations of the quadratic fluctuations of the Lagrangian. We see that some of our frequencies match with what you have here. Now, a result that I also want to highlight is that it seems that the spectrum is insensitive to whether or not you're looking at the unimodular or the non-unimodular twisted model, meaning that whether or not you are including this fermionic tail or you're not including the fermionic tail. And this is quite interesting because the non-unimodular case is not giving rise to a usual supergravity model. And so this we see for this particular solution in the twisted model. Okay, I think that brings me to my conclusions. So I looked at supergravity solution generating techniques. In particular, I looked at homogeneous Yang-Baxter deformations as supergravity solution generating techniques. And I showed you how in the formulation of double field theory, it's very efficient to see that they are that they have this feature. And this then allowed us to include a larger web of dualities and deformations with the same feature. And it would be very interesting to extend that setup to relax some of our assumptions, but also extend it in the world of exceptional field theory, heterotic DFT, etc. Also, their usage in holography, of course, will be very interesting for some lower dimensional examples to understand what is happening at the level of the CFT. Then I told you that at the same time, these transformations are also canonical transformations at the level of the worldsheet, so they preserve integrability. And using that you have such a canonical transformation, a non-trivial canonical transformation, we could see these deformed homogeneous Yang-Baxter models as undeformed models with twisted boundary conditions. I told you how you get an explicit expression of these twisted boundary conditions. I think it would be very interesting to extend this to the larger web of dualities and deformations that we know. Let me emphasize that, of course, as I told you, we really need to use these properties of homogeneous Yang-Baxter deformations, namely those two co-cycles, to really get some explicit expressions. So it might not be straightforward for other type of deformations. But maybe there is some nicer way of reformulating the problem in some first order formulation. But that's, of course, very vague. Then we use this twisted picture to extend the integrable methods and apply them to our undeformed twisted models, and in particular get a first step to tackle the spectral problem of a Jordanian deformation of ADS5 cross S5. Then, of course, a very pressing question is what happens at the holographic dual, so at the deformed N=4 super Yang Mills site. Do we have some spin chain with twisted boundary conditions, and can we match our computations with that? And so with that, I would like to conclude, and thank you.
So, thank you very much, Sibylle, for the very nice talk. Do we have questions? Right, Linus?
So what does the dilaton look like for this deformation?
For the homogeneous Yang-Baxter deformation?
For the example you were discussing, this Jordanian deformation.
Oh, that's a good question.
In particular, is it finite everywhere, or does it blow up somewhere?
I think I cannot. Yeah, I have not looked into that property. Yeah. Yeah, maybe you.
Not off the top of my head.
Yeah, it was not important for our analysis. As I said, like actually the unimodular and the non-unimodular case turned out to be the same. The whole analysis was done for the non-unimodular case, and then just right at the end we noticed that if you include this fermionic tail, it doesn't change your classical curve and the semi-classical quantization of it. So that's why I didn't really look at dilaton. Yeah.
Okay. What about the metric? Is the metric regular, or is there a singularity somewhere?
So we looked at the geodesic completeness of this model. It doesn't have any singularity, so at Z is 0, you would think that there is some singularity, but it's more like the boundary of ADS.
Thank you.
All right, further questions? Yeah.
I may have two questions. So first question is, this undeformed model with twisted boundary conditions could be interpreted as, probably it cannot be interpreted as a dynamics of closed string. No, it's something else, isn't it? So did you think about what could be interaction of such objects? Or
so like a string theory amplitude kind of
with this monodromy, yes, because you know all this old stuff of Poisson-Lie duality, you know, works well only when you cut out the zero modes. Now you enter the zero modes into the game. On one side, it's pretty okay. It's your Jordanian deformed model. On the other side, you produce this monodromy. And from the point of view of integrability, all is okay. From point of view of interpretation, so at several people at all times of Poisson-Lie T-duality didn't know how to interpret it. It's neither open nor closed string theory. So what could be interaction of such object which develop such monodromy? And so did you think about that?
No, to be honest, no. I think it's a very, very interesting question. But for me, in my opinion, like this reformulation in terms of twisted boundary conditions, the power is really in integrability, where, as you say, it's completely fine.
It's completely fine. Yes.
Yeah, and where you can really use the non-integrable methods and just with some very minor stuff, very minor modifications, you can apply it to the twisted case.
And the second question is much related, and also because in all days we studied things from the point of view of Dreamfield double, which you didn't do. But did you think about how would be this twisted boundary condition from the strings in the Dreamfield double?
Yeah, so that's what I was alluding to in my outlook. So having some first order formulation for these twisted models,
yes,
I think that would be amazing. Yeah, but I
think that it would be an interesting thing to work out.
I agree. Yeah, totally.
All right, further questions? Yeah, okay.
Well, it's probably a very simple question. Do you know how the Virasoro constraints transform under your transformation, under your twist?
Yeah, they are completely the same. So again, you can write down the Virasoro constraints in terms of these currents. Here, this is for the PCM, but it's just some particular projections of these currents in the case of the supercoset. For the undeformed case, is the projections of J tilde. And for the deformed case, it's the same projections of A. So again, you just can replace G tilde with A, and you're sure that also your Virasoro constraints are satisfied.
Right. So basically, that was the question. Yeah. When you talk only about sigma model, you don't talk about string theory. String theory also has Virasoro constraints, which has to be imposed, right?
Yes, yeah.
And when you do this transformation, it's not a canonical transformation. It's a transformation, well, you can call it locally canonical transformation, but since it changes the boundary conditions, it's not. You get two different models.
Mm-hmm.
And the question is whether this transformation can be done on the level of string theory, so that the Virasoro constraint would be still
yeah, so regarding the Virasoro constraints, this is fine. Regarding GS corrections and stuff like that, this is a lot more difficult because we are in a Green-Schwarz formulation here and stuff like that. But regarding, as I said, Virasoro constraints are just mapped to each other under this sending G tilde to A. So if you satisfy them in the original case, you will satisfy them also in the twisted case.
Yes, so my question is, so you know, you've been imposing closed boundary conditions in all of this, and if you open the boundary conditions, you know that integrability might be broken. And the question is if you've tried to kind of consider which set of open boundary conditions would be integrable and then also be projected, be also integrable in the deformed situations.
Yeah, that's a very interesting thing that you can do. And it would give you some integrable deburring configurations and stuff like that. But here it's not. So really, we want to look at a closed periodic model and compute things for that. But it's also something that is an interesting outlook direction. Yeah, I don't know if you can interpret that in some terms of twisted open boundary conditions. I have no idea how that would look like. Yeah,
probably that. But the other question is rather. So you studied the Jordanian in ADS5 courses 5, so maybe the next could be ADS4 cross CP, so ABJM kind of. So you think it's possible also? There's no kind of obstacle somehow?
So as long as thank you for the question, because I think it's a nice point. So Jordanian deformations are particularly nice because they lead to diagonalizable twists. in some particular class, up to some subtleties. But many of the other homogeneous Yang-Baxter deformations may lead to non-diagonalizable twists. So as long as you find some, I don't know, I never really looked in detail to ADS4, but as long as you have some SL2R subalgebra, which I imagine you have, you can apply such transformations. You have to, find an R matrix that satisfies these conditions of modularity in the classical Yang-Baxter equation. And then, I think the whole story rather straightforwardly goes through. You will, I imagine that you will find at the asymptotics of the monodromy matrix some local Cartan charges, and then you have to take care of like having these global coordinates and a global energy that is in this asymptotics of the monodromy matrix to really identify what is the quantum correction that you're computing. But, yeah.
Okay.
All right, then maybe I have a quick question as well, or two quick questions. So at some point you were mentioning you had a big Q and a small Q, and the small Q was 0, and so on. So it's sort of looking like your twist function only depends on one conserved charge in some way.
Yes.
But for these, like for the simpler example of these abelian ones, everything really always appears, like both of them appear on an equal footing, but here one of them disappears. Do you have like some interpretation to this? Like,
that's a good point.
That's just for that specific solution.
Yes, but
So the small q was 0, was when specified the quantized solution. So we're just considering
okay.
particular string configuration and happens to 0.
well, I think maybe because you read the
Well,
paper.
wait, then I have one follow-up question. So.
If I say it correctly, big Q acts on small Q.
Well, it's just a charge, so it's just a multiplication. It's
But so then I have a follow-up question. So these twists, I mean, algebraically you would imagine they are related to Drinfeld twists, and the Drinfeld twist for Jordanian deformation looks something like this, but not exactly. Is there is it clear that you could somehow, I don't know, pick a different gauge and get literally what you expect for a Jordanian twist, or is there something fundamental obstructing this? And if so, is there an interpretation to that?
I think I've never thought about this.
Okay, that's fine. And then one final question. This energy that depended on two parameters, A and B, is there a non-trivial choice of A and B where still the energy correction vanishes? Or is it generically non-zero for any A and B?
A something is an overall, will be an overall coefficient. And then the rest just depends on this combination eta over 2b squared, this thing. So you're asking if I have maybe let's call it beta, if this guy, if you have other values, that's a very good, I didn't try to look at this, but I imagine, yes, I mean, it's not just a linear expression, so,
Okay.
yeah.
All right, thanks. Any other final questions? No? Then let's, what? Was there one more question? Okay, Arkady, real quick.
So about this unimodular versus non-unimodular. So if you look at one loop fluctuations, so the dilaton is not important. Fluxes are important. So maybe it's just for that particular classical solution, this difference is vanishing. So it may be an accident of just choosing that particular solution that they match. Yeah.
We saw this in. So we analyze this in generality, not only for this particular solution, where you basically can factorize your twist, where the guy only, the non-trivial information is in this Q E plus. And this is under just one assumption. There's like two classes that we can look at. But basically for both of them we see that the fermionic contributions just don't enter in this class at the classical level, and therefore also at the semi-classical level. But there may be some subtleties involved for some particular class. Now, also, what I should mention is that this is we saw this for the twisted model. So, in terms of the twists, there may be up to one loop, maybe some problems if you want to. So, the equivalence with the twisted model and the deformed model is only classically. There may be, if you go to one loop, that there is some. Some problem if you want to equate them. So you should, there's some anomaly. Sorry, I couldn't think of the word. That if you want to try to equate them. Just to say that this insensitivity to the unimodularity case and the non-unimodularity case is for this twisted model. To really make a statement, you should also do a computation, some honest computation in the deformed model and compare that.
So I think we have.
Yeah, thank you.
So there's one final question, and then we should stop.
With this technique, could you say something about vector functions of the sigma model? I mean, analysis, vector functions deformed or something like that?
The beta functions?
Yeah, right, of the sigma model.
Yeah, so in this, if you take this, no, I'm going in the wrong way. So if you include this fermionic tail, as I said, like you will still have a supergravity solution. The beta functions are still satisfied. If you don't include this fermionic tail, you will get some running of your deformation parameter.
Thank you.
Because you don't have a supergravity.
Okay, so let's thank Sibylle again for her nice talk.